Warm greetings to the admissions committee at National Yang Ming Chiao Tung University. My name is Manasa Yogesh and I am from Karnataka, India. I graduated in the year 2025 with a degree in Electronics and Communication Engineering from Dayanand Sagar College of Engineering affiliated to Visvesvaraya Technological University with a CGPA of 8.76. My fascination with semiconductor devices began not just through coursework, but through genuinely questioning how the devices we use every day actually work at the most fundamental level. During my undergraduate studies, I was introduced to VLSI design both through formal courses and hands-on lab work. I had my first experience with RTL design through an internship at RF Technologies, where I developed and verified digital circuits using Verilog and ModelSim. That experience taught me the discipline of translating the specifications into working hardware. It also sparked a question in me how the underlying devices that run these circuits actually behave at the nanoscale. So that question led me deeper from the logic level all the way down to the device level. The defining experience of my undergraduate journey was my final year project, where I simulated tunnel field effect transistors, that is TFETs, and double gate TFETs using Silvaco TCAD. My focus was on analyzing how the high K dielectric materials influence the electrical performance of double gate TFETs at the nanoscale. TFETs are a compelling area of research because they operate through band-to-band tunneling rather than thermionic injection, which allows them to achieve the sub-threshold swings below the 60 millivolts per decade limit of conventional MOSFETs. Through my simulations, I studied how engineering the gate dielectric, particularly through the introduction of high-K dielectrics, can dramatically improve electrostatic control, reduce leakage, and enhance overall device performance in these structures. I also co-authored a research paper published at an IEEE conference in the year 2024 titled Effect of Channel Length on the Electrical Performance of a Nanoscale MOSFET. In that study, we used nanohub simulations to analyze how varying channel lengths from 100 to 150 nanometers can affect the key performance parameters such as drain current, threshold voltage, and transconductance using HFO2 as the high K gate dielectric. I further strengthened my research credentials through an internship at NTAF division in National Aerospace Laboratories. As a research intern, I worked on a signal processing challenge, investigating how the data block size actually influences the frequency spectrum of unsteady pressure measurements in the wind tunnel environment. I implemented MATLAB-based spectral analysis using Wells' method to validate the experimental findings. So this experience was invaluable. It trained me to build a bridge between raw experimental data and meaningful physical interpretation. My research interest lies at the intersection of semiconductor device physics, nanotechnologies, and advanced CMOS technologies. I am particularly curious about how emerging devices structures such as FinFETs, tunnel TFETs, and other devices which addresses the challenges that arise as we scale them beyond Moore's law. Managing leakage currents and controlling short channel effects and maintaining power efficiency without sacrificing the performance. For me, the most compelling aspect of this field is that fundamental nanoscale research does not remain theoretical. It directly enables transformative technologies in AI accelerators, high-speed communications, and energy-efficient computing. That connection between device physics and the real world is what drives me. I choose NYCU because it is one of Asia's foremost institutions for semiconductor research, and its research direction aligns precisely with my own. I was particularly impressed by NYCU's work in areas such as ultra-high density nanoscale transistors, advanced gate dielectric engineering, and high frequency device development. So these are exactly the problems I want to dedicate my graduate research to. NYCU's deep connection with Taiwan's semiconductor ecosystem, including industry leaders such as TSMC and MediaTek, also represent an extraordinary opportunity to ensure that my research has both scientific rigor and real-world relevance. I believe this environment will challenge me, will shape me, and allow me to contribute to the global semiconductor research community. I bring to this program a solid foundation in device physics and simulation, a research experience in device level and circuit level, a IEEE publication, and a genuine passion in understanding how the matter behaves in its smallest scale and how understanding that will change the world. I am deeply grateful for your time and consideration, and I am truly excited about the opportunity to learn from NYCU's distinguished faculty, to contribute to its research community, and to grow as an engineer. Thank you so much.